basic public key crypto. So what's missing from this scheme?
Key distribution.
Key distribution, right? I mean, public keys. All right, I somehow had to have the Purdue EDU key to authenticate the record. Okay, maybe I'm configured with that. But how many DNS zones do I visit? You know, of the billion records, we're divided into several tens of millions of zones. And chances are I don't have the public key for every one of those tens of millions of zones. So I need a good public key distribution system. Here we have a nice advantage. We already have a natural hierarchy. If we assume that everybody knew the root key, which is not such a bad assumption, because right now everybody who's a cache has to know the IP addresses of the root servers. That has to be hard-coded. So now we're going to hard-code in a root key. If we knew the root key, and we have a rule that every parent signs their children, we can actually build the system, and starting from the root, we can walk down the tree and find any DNS record we want. So if I want to authenticate www.purdue.edu, I'm going to start from my well-known root key, and I'm going to ask for, you know, what's the public key for edu? What I'm going to get back is the edu key plus a signature from root. So now I can authenticate edu. With the authenticated edu key, I can go off and I can ask for the Purdue edu key. Purdue edu is signed by its parent, edu. So now I can authenticate Purdue edu key. And finally, the record I want, Purdue edu IP address, or its A record, is signed by the Purdue edu key. So I have a nice authentication chain starting at the root, walking down to edu, walking down to Purdue, finally walking down to the data I want. Make sense? Okay, so this is all, you know, something that you would expect almost an undergrad crypto class to come up with, right? I mean, this is not rocket science at this point. This is basic cryptography. The way we actually put it into the zone is, you know, not much. I mean, this is just to give you a sense that this is really a standard. These are real records. So here what I have are the A records. And below the A record is what's called the RR-SIG record. So the new resource record signature. And this signature has an inception date of October 27th, 2004, an expiration date of November 26th on 2005. So that's when this record is valid for. I know who signed it. It's signed by a key named Purdue edu with tag 468. So if you find that key, you know how to authenticate the data. How do I know that's the right key to apply here? Right, so this signature basically tells you, here's the signature for the record you're asking for. And the guy who signed it is the guy in red, key 468 from Purdue edu. What if I could sign this with any public key, right? I could sign it with foo.com or, you know, darpa.mil, name your favorite zone. So how do I know this is the right one? I mean, it follows almost directly from the name, right? I mean, who gets to sign the Purdue edu information? The Purdue edu zone. So I have to be able to assert that Purdue edu is actually in the Purdue edu zone. So to do that, basically, I need to go to the edu people. I need to get the existence of a Purdue edu key that's authenticated proves Purdue edu exists. And now I can ask Purdue edu, have you delegated this away? If they've signed it, they haven't delegated it away. If they've delegated it away, instead of getting a signature here, I'll get a referral to another key that's signed by Purdue. So I can distinctly draw a zone boundary and tell who should sign every record. I can also store the public key in the DNS. Since it's public key crypto, I don't care who knows it. I want to make it publicly available. So in addition to sending you back the answer, I'm going to be nice, and I'm also going to send you back the key that you can use to authenticate this and the signature. And of course, the important part of the signature is that it's signed by edu. So if I knew edu key 569, I can authenticate the Purdue key. If I know the Purdue key, I can authenticate the www record, and I'm done. Recursively, I can authenticate the edu key from the root key and back up all the way to the top. Make sense? Still, you know, nothing new here. So we will add one little trick that's worth actually, you know, some some note, and you probably have to scratch your head a little bit to figure this one out. So what if I ask for a typo? Purdue.edu. So I basically, this answer does not exist. And I want an authenticated proof that guy doesn't exist. The challenge is the private key's not available. Right? And that's there for a very, very good reason. The way we've deployed DNS, if you're running DNS correctly, not all of the Purdue EDU servers sit here at Purdue. Because if they do, a single network failure takes them all out. The servers should be spread apart. A few companies, large software vendors have learned this kind of the hard way by putting all their DNS servers on the same subnet or behind the same switch. But essentially, if you spread out your DNS servers, you've got great robustness against network failures, but spreading out your private key isn't such a good idea. So if I have Purdue servers, 2 sitting here at Purdue and 1 sitting off at Hopkins, I'm maybe okay putting my private key on the master server at Purdue, maybe okay putting the private key in the backup, almost certainly not okay giving the private key to Hopkins. So I can't have the private key at the server. Also, if I do put the private key in the server, in addition to simply the distribution problem, now I'm asking the server to do new computations. I'm opening up potential holes for distributed denial of service or simply added load on the server. So there's no private key. No private key at the server, but I still need to prove to you Purdue doesn't exist. Now, I can't just have a generic record that isn't tied to the name. Whatever you requested without specifying the request doesn't exist. Because if I do that, what's the attacker going to do? Replay that when you ask for a legitimate name, like right? So I've got to somehow tie it to the name, and I don't have the key online, and I don't know you're going to ask for . Actually, maybe I know you're going to ask for, right? Maybe that's a common typo. But how many typos could you possibly put in? Well, that's pretty much an unlimited set, and I'd like to give you an affirmative yes/no answer for any query you ask for. So given this, what do? Here's the query, Purdue EDU. Doesn't exist. I need to prove it. I have a public key system, but the private key is not online. You didn't know I was going to ask for this record. Anybody have an idea on how you can actually prove this thing doesn't exist? Okay, so the solution actually is not immediately apparent, but will be entirely trivial once you see it. So here's the idea. I know what's in the zone. Let me, instead of trying to authenticate what doesn't exist, let me order the zone in a nice canonical order, essentially alphabetical order, plus a little bit to handle DNS issues. And now I can tell you something like, for instance, in the zone file, there's some entry at u.purdue edu, and the next entry is at . And I know this ahead of time, and I can sign this ahead of time. So if you ask for anything in the range between u and . I can just replay this signed message. Make sense? So what happens is along comes the resolver. He says, I'm looking for Purdue edu. It goes off, and what I get back is an answer. This doesn't exist. Can't sign that part of the message because it's sort of dynamically generated. Plus, by the way, there is a name called u, and the next name after u is . That's pre-signed. That's already loaded in the server without having the private key online. That's returned. If the answer you looked for did exist, this wouldn't be the interval. If did exist, it would say u, the next name is . Make sense? Yeah.
What if your domain, people change their DNS records, right?
Ah, yes. So if you change the DNS records, you better change the corresponding NSETs.
When you're required to change your key, too. Because, well, let's say I start out with A and C, so now my server is returning back something that says, okay, there's an A and there's a C, and I request B, there's no B. Well, later I add a B. Well, I've already returned that packet. Someone could replay that and deny service to B, right?
Yes, somebody could replay that. So there is, and in fact, we'll come to some of this issue later, is one thing DNS Set chose not to do is have either revocation or essentially support a very much real-time update. What I'm bound by is the lifetime of this signature. And if this signature is for 2 years, then I certainly can withdraw it from my zone, and that's not going to stop the attack. Right? For the next 2 years, anytime somebody asks for dub, the attacker can replay this old answer and say, sorry, it doesn't exist. And I'm vulnerable exactly for that time. So that's bad, right? But why is that not such a big deal for DNS?
Short list times.
Yeah, we can put in short lease times. I certainly don't have to change keys. I just have to re-sign, right? There's no changing the key. There's just keeping a short lifetime on this guy and re-signing him. And DNS was never designed to be a real-time system. In the current DNS, there's already a TTL in there. The zone file gets transferred from the master server to the secondary server. You may query any of those servers. You may hold it in your cache. So if you were hoping you're going to add dub Purdue EDU, and it's going to instantaneously appear in the DNS, you were already out of luck. I may be making it worse by putting a longer signature lifetime on here. But I'm certainly not introducing a new problem. And depending on how frequently I'm willing to re-sign the zone, I can chop this down. Ideally, the time here is the expected TTL on the record time. So for a very dynamic zone, I'm going to be doing a lot of re-signing. But that's definitely a limitation of the system. Any other problems with this kind of approach? Would you be willing to deploy this on your zone? So we can get into a sort of philosophical debate on security through obscurity. What's one immediate consequence of these NSET records? If I want to find out everything in the Purdue DNS, and the Purdue DNS is exactly n entries long, how many queries do I need to figure it out? Exactly n queries, right? I will query for Purdue EDU. It will tell me, here's Purdue EDU. The next record is a.purdue edu. Now I'll ask for the NSEC record in A. I'll say, give me the A NSEC record. It'll say, the next name after A is C. The next name after C is D. And I've exactly enumerated the zone file. So now we have a debate as to, is that a bad thing? And the answer, at least in the standards community, is no, it's not. The answer in the operational community is still yet to be determined. If you go to Black Hat, the first thing they talk about in the Black Hat DNS thing is look for zones that allow zone transfers. You can get all of Purdue's host information. You can, usually from the name, probably Christina identifies her boxes with similar names and maybe has a particular pattern for patching the boxes. I do the same thing. And looking at the zone file, there's a whole host of social engineering you can derive from that. You know all the hosts, you know all the data. Now, even if you've turned off zone transfers, I've essentially turned it back on for you. On the other hand, this is public data. I mean, if the security of your system was relying on the fact that I couldn't figure out there was a machine called u.purdue edu, I'm not convinced you really had security in the first place. And in fact, since I know your IP address space, I can use the reverse space with more queries, but still in deterministic time, to identify basically all your machines that have an IP space within Purdue's allocated range. And I can't necessarily get the entire DNS that way, but I can get essentially the effective one. So I've introduced essentially, I've essentially revealed your zone to the whole world. And in the standards community, we've decided, you know, the right thing to do is to say security through obscurity is not security. So you don't get it. You wanted it, too bad. You shouldn't have had it in the first place. Whether the operational community will sign on is still in the to be determined stage. Okay, so, but that being said, it's a nice system, it's clear and all, but there is no magic crypto fairy dust. Even in DNS Set, this system took 10 years to standardize. And let me give you a few ideas why. We started off with key management. And key management in any large-scale public key crypto system is going to be essentially a practical killer unless you can do it well. The way we started off by doing it was saying we got this great hierarchy, right? And we're going to have EDU sign the Purdue key. And then we're going to put that signature in the Purdue zone. And now we've got a nice chain of trust. You can start from the root, you can walk to EDU, you can get from EDU to Purdue, and so on. And the only problem now occurs when you try to go and change the key for EDU or conf. So VeriSign loves this problem. VeriSign runs the conf zone. Suppose I deploy this system and I need to change the key for conf. Who do I need to update? All 30 million star.com zones. Right? I have to, because everybody has a signature by the key I'm about to replace. So before I can replace it, everybody better have a signature from the new key, otherwise I'm potentially going to cut them off and make them appear like a spoofed zone or worse. So now I've got a real problem changing the key. And you can imagine the VeriSign people looking at this standard and saying, our lawyers love this, right? I want to change the key Monday. Cisco comes along and says, sorry, we have some internal thing, we can't change by Monday. Amazon comes along and says, yes, I agree with the need to change the key. The actual com key might have been compromised. To preserve our e-commerce business, you better change the key. So, do you chop off Cisco or do you chop off Amazon? Both of them have a lot of lawyers. You're not going to win either way. And it's not a situation that VeriSign wants to be involved in. So we need essentially a different operational system. This system it was originally developed by the military where this made sense. You have a top-down authority. The top guy can say we're changing keys. The guy below him will do it. But in the commercial world, in a real distributed system, this doesn't make sense. So sort of the graphic of how you change the key is this. This is the coordination problem between EDU and one of the children, or between COM and one of the 30 million children. The first thing Purdue EDU does is send its key up to the parent. The parent sends back a signature using its key P1. When I want to change to P2, the parent first has to add P2. It's got to go to its parent, get a signature from its parent saying, yes, it's okay to add P2. Then it's got to start shipping out P2 signatures to all the child zones. After they've acknowledged that's been replaced, we can actually go ahead and replace P1 with P2. Then we can actually remove the old P1 signature from the zone. And remember, all these guys have lifetimes that need to be refreshed or restored. And if we're running up against the end of a lifetime here, this entire thing can be compressed, or potentially require signing with an old key. And I'm doing this 30 million times on 30 million different sets. So the main change in the standard between 2035 and the current one that came out in February is really all in the key management. Most everything else is details. What we've done is we've just done the standard computer science trick. A layer of indirection is going to solve anything. We took the SHA-1 hash. The fact that the SHA-1 hash only saves us room. You can think of this as simply taking a copy of the child key, storing it in a different record type at the parent. We call this the Delegation Signer or the DS record. We take that up at EDU. The DS record is stored solely at EDU, is signed by the EDU key. If EDU needs to change keys, it simply re-signs the data at its local zone. The child zone, Purdue, needs to make sure that it has at least one key in its set that matches this DS record. Because the resolver is going to authenticate the DS record and say, I'm looking for a Purdue key that matches that DS record. If it finds that key, it's happy, and you can't forge that. If it doesn't find that key, then we believe we've been directed to a false zone. We can also add additional keys. If we change this matching key, then we do have to coordinate with the parent, but it's a coordination problem going up instead of down. Purdue needs to notify EDU. There is no pipe coming down where an EDU change needs to notify Purdue. And you only have one parent in the tree, so if I only have notification going up, that works. I can also generate additional keys that might be used to sign the data. So now I can actually have one sort of long-lasting, extra secure key that matches the parent, and one frequently changing zone signing key that I can change on a whim without notifying anybody else. So in terms of pictures, it looks like this. What we have in the current DNS is zero security. Up here at the EDU servers, they've stored some records that say Purdue EDU, their name servers are here. Down at Purdue, we just have the Purdue data. What I'm going to do is I'm going to add in a public key for Purdue, and I'm going to sign all the data with this public key. So I've got a bunch of signatures by that. Now I need a way to authenticate this public key. What I'm going to do is add a second public key, and I'm going to sign public key number 2 with public key number 1. Actually, in DNS, all I can do is sign RR set, so I can sign the set of all keys. So now if I knew key 1, I could authenticate any zone data. Because if I knew key 1, I can authenticate key 2. If I know key 2, I can authenticate the data. So now I just got to figure out a way to learn key 1. I take a copy of key 1, put it up at the parent, and sign it by EDU. Right? So now, instead of just getting a referral to the Purdue name servers, I get a referral to Purdue name servers, plus I get the DS record that says when you go to these name servers, you ought to find a public key that matches key 1, pub key 1, the green guy. And the reason you know this is authentic, at least it's authenticated from the point of EDU, is EDU has signed this information so the attacker can't point you to the wrong place unless the attacker had the EDU key. Now you go down to the Purdue name server, you say, give me your keys. You look for somebody that matches the green key 1. You find it. You know that's authenticated. That authenticates the blue key. The blue key authenticates the data. You're done. So what did I gain by this? One nice thing I gained is if I want to change the EDU key, nobody tells Purdue. All I have to do is update this black signature up here at the top. So zero coordination if I want to change the Purdue key. The EDU key. If I want to change key 2, then I don't need to notify EDU. All I've got to do is replace key 2, re-sign the new version with key 3, and I'm done. So I can do distributed disjoint key management. This is, again, not rocket science, but now there's a little bit of operational complexity. This makes sense? So what if I want to change key 1? How do I change key 1? That one I can't do without coordination, right? Because if I pull out key 1, everything's going to break. And I claim I can do this actually by only storing one DS record at the parent at any time. And here's how we do it. We start off, so key 2 is no longer important. So let's focus just on key 1. And what I want to do is replace key 1 with the colors aren't quite as different as I would like here, but with the key 3, the purple key. All right, so I started in this stage, resolvers work, no problem. The first thing I do is I add my new key, my key 3, into the Purdue zone. And I haven't coordinated with anybody. I've done this solely at Purdue. And I've re-signed a set of keys with both key 1 and key 2. So if you knew key 1, you could authenticate the set and believe key 2 and key 3. If you knew key 3, you could authenticate the set and authenticate key 1 and key 2. So far, so good? Okay, now that I've got this in place, I'm free to, at a slower pace, ask my parent zone, EDU, to change the DS record. So now I have some out-of-band secure communication with my parent, which I already have because I need to occasionally change my name servers, so I'm not adding a new piece into the system. And I talk to EDU and I say, hey, I'm planning to change from key 1 to key 3. Here's my DS record, please sign it. So Purdue adds that in, so EDU adds that in, signs it with the EDU key, and I claim it still works. And I claim I don't care when that change happens. Because key 1 is still working. Well, they have the DS1 record. People go to my zone, they find the green key, they authenticate key 2 and key 3. After the change, they go to my zone, they find the purple key, they authenticate key 1 and key 2. So this change can happen seamlessly. It can roll over kind of gracefully. I can handle TTLs. I can handle timeouts, all that kind of thing. After I wait a little while, finally for all the caches to catch up, all the signatures to expire, the old DS record for key 1 to be flushed from the system, after that's safely occurred, I can now pull out key 1, and I'm at this set that just involves key 2 and the new key 3. So I've done the change, and the only active step I had talking to the parent was sending a secure message to the parent saying, replace DS1 with DS3. And I don't care how fast you do it. I'll just check by sending a regular old DNS query and checking whether you've done it or not. So it scales nicely. It's actually deployable. This can actually be rolled out in the real DNS and is supported in fact, it's supported in bind. It's deployed in a few zones. COM has it essentially ready to run modulo some billing issues, and a few top-level zones have deployed this, especially in Europe. So in Europe, we're actually running some secure DNS zones at this point. Okay, so yeah.
Can this really solve the problem with just like in two companies? One wants to change the key immediately, the other wants to wait for a while?
So the big question here is, how quickly can you do a key change? Right? If this is a planned key rollover, no problem, right? If I have sort of a plan to move from key 1 to key 3, I do this step. The timing isn't so important. All I need to know is that, say I want to change on November 1st to the new key. Well, sometime in late October, I add the new key in. I send the record to the parent zone, and I hope by early November they've changed the key. What if key 1's been compromised? That's your concern, right? So I need to change it immediately. I can't do that. I claim that I don't need to do that, or that actually doing that won't help. Because even if I change it immediately, the attacker who compromised the key is going to go fetch the old DS record with the old signature lifetime from the EDU key, and is going to continue replaying it. So the speed at which I can pull these things out of the actual servers is totally irrelevant. The vulnerability time period for the key depends on the lifetime of that signature at the DS record. So you're right, I can't do an immediate key chain. If a key is compromised without key revocation, which is actually a good open problem for DNS Set, I'm basically stuck with the lifetime of the DS record.
But that can be quite a serious problem potentially.
Yes.
In the attack, right?
Especially if this is the root key, right? I mean, if this is the root key, the game is over, at least until that key expires. So key compromise, in fact, one of the things we're looking at now is how you actually do key revocation. And so this is, in my view, a nice MS thesis kind of problem. We've got an existing system, now I want to do key revocation. Potentially, maybe it's more than MS thesis if it gets kind of tricky, but in theory, we should be able to revoke a key. We didn't add that into DNS. Essentially, the standard, it just didn't make it into the standard. There is an agreement on how to do it. But you're right. And there is this sort of naive thinking that still kind of permeates the standard, which says, you know what I'm going to do is I'm going to quickly pull them out of the zone. Yeah, so the focus is on, let's try to speed up the key change rule. Right? So I'm going to put time bounds on how fast the parent must respond in the event of a compromised key. And yes, for the real server, I will flush the compromised key out real quick. But flushing the key out of the attacker's hands is always the harder problem, right? And it really doesn't matter how fast I can change the authoritative servers unless I can revoke the key. Well, why not just do key? What would you do for key revocation? The problem is you don't know who has the key, and think about the scale you have here. We're talking in COM alone 30 million keys. And so key revocation lists have a problem of scale plus who signs them. Following the compromised hierarchy gets you into a chicken and egg kind of problem. The hierarchy's been compromised, so plus now I have to pay an overhead of checking for the compromised key. if I even know where to check. It's doable, but it's not necessarily trivial. So I think it's solvable, but it's not sort of, you know, by the end of tonight I'll have it done. By the end of this week, maybe I'll have it done. But at the end of tonight, I want it done. Another problem we had in terms of the standard and getting this thing deployed is the way we set up existing DNS is we took the parent, EDU, and it stores the NS record that tells how to reach the child. And we called those things NS records. At the same time, who really knows what the Purdue servers are? Who's got the authority to determine the Purdue servers are X, Y, and Z? Purdue, right? Who needs to have that information in order to get to Purdue? The parent, EDU, right? So you have this sort of limitation in the existing DNS where Purdue determines who the real servers are. But if EDU doesn't know who they are, it does no good. Because I don't know the Purdue servers, I'm going to go to EDU, I'm going to say, where are they? The Purdue EDU is going to say, I think the servers are X, Y, and Q. I'm going to go to server Q, it's going to say, I'm not a Purdue server. Something must have gone wrong at the EDU side. Does that actually happen, you think, in the real system? Frequently. We have a SIGCOMM 2004 paper that actually compares perceived theoretical robustness of the DNS with actual robustness of the DNS after you take into account misconfigurations. Well, user performance actually isn't that badly impacted because DNS is very robust. As long as one server works, you'll get your answer. And you'll pay a few extra milliseconds, but you won't really notice in your web browser. The actual redundancy of the system, if something fails, is far less than what the administrators would like because of this conflict. So we have this redundancy limitation. But more importantly, we have now the problem of, now that we're going to sign it all, who signs the information? Since the information in DNS is exactly identical, once it leaves that server, you don't know whether it came from the parent or the child. It's just the NS records for Purdue. So if you have the parent sign them, and the cache gets the parent version, there's no way to flush it out and get the child version. So we have a rule that says, look, the parent can't sign. It doesn't belong to the parent. The child has to sign them, and that creates somewhat of a limitation. So what's the, security-wise, what's the problem with this? So I go to EDU. In fact, back one slide here. Or 2 slides. I go to EDU and note that NS records were never signed. So as the attacker, what can you choose to do? You can send the valid DS record. You can go to EDU. You can get the valid DS record with a valid signature. You can send that plus a bunch of false server names pointing to whoever you want. And what will be the end effect on the resolver? Will the resolver believe those are the valid servers for Purdue? It will try asking them about Purdue, but the first thing it will ask them is it will say, give me your DNS key. And that false server has to give the real DNS key, otherwise it won't match the DS record. So you can go to the false server, but the false server either has to send the wrong key, in which case he's revealed as not being the right guy, or send the real key, in which case I haven't done any harm. So either I'm either going to report the right data, in which case it's fine, I got redirected to the wrong spot, or I'm going to report the wrong key or the wrong signature information, and it's going to be revealed that that's an attack. The only problem is I don't know who attacked it. I ask EDU, what are the servers for Purdue? It says the servers are Q, R, and S. I ask Q, Q doesn't have the right credentials. I ask R, not the right credentials. I ask S, not the right credentials. I know at this point I can't get the desired Purdue information. I don't know whether it's the fact that somebody's now playing man in the middle between those servers, or whether EDU didn't direct me to the right spot, or what happened. But what I've done is I've added a denial of service attack. I haven't added a misdirection attack. How important that is, somewhat, at least I haven't misdirected you to the wrong website. I've told you I can't get to the website you want to find, which for DNS is still fairly severe. But I have this limitation, and essentially it's solvable in the DNS. But to solve it, whoa, okay, too much animation there. But to solve it, I actually have to fix the original problem with the DNS, which is that I have the same name for the glue records in both places. If I name them differently, then I'm okay. Just to give you one more story on why things happen to break in the standards process is, so we built this. We actually standardized it. We were close to last call on the standard. We had an interop workshop. Various big vendors came. We ran it, and we discovered we added a great little denial of service attack. So here's the new trick. I've got this DS record that says what's the Purdue key. And it's stored at the parent. But every other Purdue record is actually stored down at Purdue. I could store the DS record and its signature down at Purdue, but now I've reintroduced the coordination problem. So I only have the DS record at the parent. If you go to Purdue and ask for the Purdue EDU DS record, what should it reply with? Mine made a sensible choice, which said, don't ask me, ask the parent. But protocol spec-wise, you don't say, don't ask me, don't ask the parent. You say, I'm not authoritative for the record you want. The resolver hears, you're not authoritative for Purdue EDU records. So what we were able to do was then send a series of queries. So you ask the resolver to look up the DS record by contacting all the Purdue servers. It contacts Purdue server 1. Purdue server 1 says, I don't have the DS record. So the cache marks that server as not valid for Purdue. You ask server number 2, do you have the DS record? It says, I don't have the DS record. The cache marks that server not valid for Purdue. I can do this for each server, mark each server not valid for Purdue. Now when somebody comes along and asks for www, the cache already knows all the Purdue servers have already said they're not valid. There's some misconfiguration. You can't get this answer. So even a trivial thing, adding a DS record, gets messy when you do the actual complication, when you do the actual protocol. And what we need is simply a different return code message that won't confuse previous resolvers, but will tell DNS Sec aware resolvers, go ask somewhere else. So essentially, I want to make it look like, no, this record doesn't exist. Yet if you know DNS Sec, go look up here. Okay, so what we have left, and so I have just a few minutes left here, what we have left is key revocation, like we talked about a little bit. Right now, we rely solely on SIG expiration dates. That's definitely a problem. We need a way to revoke compromised keys. We have incremental deployment. This whole hierarchy works great when my parent zone deploys DNS. Doesn't work so good if COM decides not to deploy. Because now I've got 30 million guys with nobody to sign their key. Also, I want to support dynamic update. I did all this work to keep the key offline because I don't trust the server, but current DNS, when my laptop gets a DHCP address, I actually send an update to my server back in Colorado. It updates the DNS. That works fine. That's a widely used feature now in DNS. I've got to support that. How do I support that with the key offline? And the last thing I want to talk about in just the last 2 minutes here is availability. So the way I've solved availability is I've put multiple servers in different places. So you kill any one of the servers, everything's okay. In particular, you kill any one of the 13 root servers, not a problem. There's 12 more to take its place. I distribute the servers widely, so any particular network fault won't kill me. I tolerate configuration errors because I work as long as one of the servers at the parent matches to the actual thing at the child. As long as one of those works, it's fine. But of course, when you look at the tree structure from a security point of view, there's this glaring thing at the top here, where 13 servers. Take those out, you have a very disproportional attack. You've just killed the entire system. But actually, I'm going to claim that's not a problem. The one I'm worried about here is this middle guy, the COM servers, because he's got 30 million zones below him. And that's where I'm going to get in trouble. Purdue has 5 servers, and yes, in fact, I can take out anything if I do enough DDoS. But the The bugaboo always in DNS is, oh, I'm going to kill the DNS servers. We don't care. Kill the DNS servers, doesn't matter. The DNS servers point you to, at most, 300 zones. The common codes, com, edu, net, org, etc., plus 200 some country codes. That information is also well published, well known, it's easy to obtain. In fact, my resolver already knows how to get to com, edu, net, org. That's probably the first thing it figures out when it wakes up. If you DDoS, yeah, I might get unlucky that my entry for com expired right as the DDoS started, or while the DDoS continues. But even if that unlikely event happens, I can always go find this information from relatively easy static public databases. I can replicate the root zone a lot of places. In fact, this is done. If you go to any operations center of major ISP, there's actually a static configuration for the root zones that can be plopped in case any of the root servers are taken out. It's a fine target to shoot at. You know, it'll make the Washington Post when you kill 9 out of them, but it won't actually damage the internet in any meaningful way. Blow away com or org or net, you've done some damage. Because unlike root, where there's 300 people sitting below me, there's 30 million sitting below com. And the chance that I've cached all those, or I can easily go look up all those, is not a trivial problem. So it's the com that's the real one. And this is where a lot of activity in both the operations and research community is. The research community has taken attack of distributed hash tables. And you can look at the recent SIGCOMM. There's an entire section in SIGCOMM 2004 dealing with this kind of approach that says, let's throw away this whole structure. Let's apply a DHT. The DHT will tell us what the servers are. Now I have a proportional attack. You take out some servers, you take out some zones, but there's no central root authority at the top. But this actually isn't going to work. And the reason it's not going to work follows some of the reasoning for DNS Set. It's a great, simple idea. I mean, if I tell you I'm going to put public key crypto into the DNS, I mean, you're going to think that's an undergrad course project at the best. You know, it's not that hard. Similarly, DHTs, when you throw away the complexity of the real distributed system, it's not that hard. Now the DHTs are trying to deal with the problem of Google actually wants to control where their servers are. And other people don't want to randomly wind up with Google. Right? So not all servers are equal. How do I control this thing? What we have in the end is DNSSEC. So this would be my... So where are we going to go in the future? What we have at this stage is we have DNSSEC that works for the most part with some nice open problems. Key revocation, and some of the other issues we discussed. But this isn't going to be enough to motivate deployment. What it really does is it enables us to look at other cool features like DHTs. Those DHT papers immediately assume DNSSEC. Because once I have DNSSEC, I can say, the actual server doesn't matter anymore. I have a credential I can verify, so now I've got a lot more power. With that power, I don't think you need to go to DHTs. If you want to be simply operational, we've actually got some studies that show if you simply increase the TTL on the name servers, not the records, which change a lot, but the name servers, which change rarely, you will not create any black holes due to changing records. Yet if you DDoS the com servers for a long period of time, weeks, you will lose only 3% of your queries, because queries actually tend to be fairly localized, and with long caches, you can keep these in your database. So now, instead of trying to solve this massive DDoS problem, I've got to figure out how to get the remaining 3%. But they're out there somewhere, even though I can't get to com. Some cache has them, or somebody has them. So the open problem in DNS right now is to take the fact we have crypto, and now consider the more serious problem of denial of service, and see what we can do. So if the last thing to take away is just, I think DNSSEC is an interesting technology. It's a nice case study on how to deploy crypto in a simple system. If you want to take it further, say, this is a good tool. How can I use this tool to solve data availability and other problems within the DNS? And there's some room for some interesting research there. So I think I'm over time, but I'll stick around if there are other questions.
Yeah, if there are questions, let's move out in the lobby out here, because we have a class in here right after this one.
Okay.
Thank you.
Okay. Oh, thanks.
Hey, I got blew a fuse.
Oh,
I had to run back across campus and hook this up, so
I have
I
a
missed the
question.
first 2 minutes.
Oh, okay. Good.